Okay, so this is the function, right? Ben? And we need to find the Laplace transform of this function using the definition. So if you remember what that definition was? Uh, the definition was f of s is equal to the integral, right? From 0 to infinity, e to the minus st. I will use s as this triangle so we don't confuse it with the 5. E to the st times f of t dt. That's basically our definition. No? Okay, so it should be a fairly straightforward mission here. Yeah. So then if we plug this in, we get the integral from 0 to infinity e to the minus st, and f of t is t e to the minus t and dt, and we can combine these two exponentials here into one exponential. Yeah, so this becomes 0 to infinity, right? Or we can relabel that infinity as b, as we do in improper integrals in calculus, and then we can combine these two exponentials into t into minus s minus 1 dt. And now this, of course, and then when we're done, we take the limit of this answer as b goes to infinity. And do you remember how to evaluate the integral of t e to the t into minus s minus 1 dt? This is by parts, right? This needs by parts. Okay, so let's go ahead and do it. So you remember how to label, yeah? U is t, and dv will be e to the t into minus s minus 1, which makes du to be dt and v to be the same, e to the t times minus s minus 1 divided by minus s minus 1. And now the integration by parts says the integral of u dv is equal to uv minus v du. That's by the by parts formula. And now we're going to start plugging them in. So if we do that, we get the integral d e to the t minus s minus 1 dt is uv, which is equal to t e to the minus to the t into minus s minus 1 divided by minus s minus 1 minus the integral of v du. So the v du. So this will be, I can pull the minus s minus 1 out because it's a constant. And then we will have e to the t into minus s minus 1 dt. And then that, of course, becomes t e to the t into minus s minus 1 over minus s minus 1 minus 1 over minus s minus 1, and the integral of that is itself divided by another minus s minus 1. This here is an s. And now we will evaluate from 0 to b. Okay, you're writing, man, you're doing this? So this becomes b e to the t into minus s minus 1 over minus s minus 1 minus, now here we have minus s minus 1 square times e to the, I should replace this with b into minus s minus 1. So this is the first part where we plug in the b, and now we evaluate at 0. So 0 will make the first term 0, and then the second term will be a 1. So this will be minus s minus 1 squared. And now we will take the limit of this as b goes to infinity. Okay. Now I could rewrite the first term as, leave this out, and this is the same thing as b over e, make it positive, so this is b into s plus 1. And then we will take the limit of this as b goes to infinity, and the other one is minus s minus 1 square, and same thing here, we'll bring this down, so this is e to the b into s plus 1. And the exponential grows much faster at infinity, provided of course that s is a positive number, than the b. So this term here will go down to 0, right? And of course 1 over infinity here we will get also 0. So both of these terms will go to 0, and then all I have left is the last term, so plus 1 over minus s minus 1 square. And here I don't have a b, so I don't have to take the limit. So we end up with 1 over minus s minus 1 squared. Right? So that means that the Laplace, and by the way, I could just rewrite this, so I can say the Laplace of t e to the minus t turned out to be 1 over, since it's squared, I could just equally likely write this as s plus 1 squared. Okay? You get the idea here? Where are you? Are you working it out? So we got this using the definition of Laplace. Of course, the only other thing that we need to mention here, by the way, is for this limit to go to 0, the exponential on the e has to be positive, right? Which means what I'm saying is this term here, right, has to be positive.
Yeah.
Which means s plus 1 has to be greater than 0. Otherwise, if it's negative, then this will blow up and the limit will not go to 0.
Yeah, because it'll come out positive.
Because it'll come out negative otherwise, and if it goes up there, it becomes infinity times infinity.
Yeah.
Okay, and the same exact argument here. If s plus 1 here is negative, then this term will become infinity. So for these two limits to go to 0, s plus 1 has to be greater than 0, which makes s greater than minus 1. Which answers the second part of the question, that the domain of the Laplace is such that s is greater than minus 1. Okay? So keep that in mind as you use the definition. You have to conduct those limits appropriately so that you get a guaranteed Laplace. So this is the domain of the Laplace, greater than negative. Questions? So are you doing this smoothly? Are there?